Hey everyone, wanted to talk to you about what, in my opinion, is one of the most important concepts in calculus, and that is derivatives. You may have heard that word before, but you're going to hear that word a lot this year. I want to explain what a derivative is, and specifically I'm going to give you the limit definition of the derivative. And we're going to be talking about derivatives all year long, and it'll eventually lead us to antiderivatives and integrals, which are a reverse process of derivatives. So the entire course is derivatives, really. And let's kind of like get into it. I'm going to try to give you a simplified version of the limit definition. So if I were to ask you to find the slope of that line, pretty simple. You'd go back to, like, I don't know, middle school or whenever the heck you did it, where you know that the slope comes from the equation y2 minus y1 over x2 minus x1. And I would give you 2 points, you would plug them in, and you would just simply find the slope. Easy enough. So I would have to give you some values down here on the x, give you some values on the y, and you just find the slope of that line. The slope is consistent throughout the entire line. But what if, instead of a line, I gave you a curve, and I asked you what the slope was? Well, the slope's not consistent. The slope is always changing. Like, at first, this line is not as steep as it is at the end of the line. And slope is just the steepness of a line. So, what I could do is say, take a tangent line, and whatever the tangent line slope is at that point kind of parallels or mirrors the slope of the red line. I could say the slope is whatever the slope of the red curve is the same slope as that tangent line. But the tangent line here is different than the first tangent line slope. This third tangent line slope is even different, and the fourth one is even more so different. And you can see each tangent line is getting steeper and steeper and steeper, so then the slopes are getting bigger and bigger and bigger. So it's kind of hard to answer the question, what is the slope of that red curve, because it's consistently evolving, getting steeper and steeper and steeper. Okay, what if I wanted to know the slope at just a very specific point? Like, what if I wanted to know the slope then just here? Okay, well, again, I could find the slope of the tangent line at that point. And what I'm trying to do is, if you remember, tangent line hits a curve just one time, I'm just trying to like parallel the instantaneous rate of change at that point. Okay, well, here's how I'm going to handle that. I'm going to put a second point on here. If I placed in a line and I could find the slope of this blue line, that could be a good estimate for the slope of the tangent line originally where I wanted it to be. Now you can see the slope of the dark blue line is much steeper than the slope of the light blue line, so that would be a bad estimate. But I could do that. Okay, let's do that. Let me put some more information on here. Let me say that this is x, and that's where I want to know the slope of the red line at. I'm going to use the slope of the secant line, the blue one, to estimate that. So let me then arbitrarily move to the right some distance. Let me call that h. That's where my second point is going to be. So this is x plus h, whatever that horizontal h distance is. If I went up to the graph, I would have my y values. I don't know if this is y, so let's just call it, in function notation, f of x. So then this is the point, the first point here, this first black one, is going to be x, let me switch colors, I apologize, x, comma, f of x. You went over some x amount, you went up some y amount, x, comma, f of x. And then the second point, from 0, 0, you went over x plus h, and then you went up to the function at x plus h. So now I have coordinates for those two black points. I can use those coordinates in the slope formula to calculate the slope of that blue line, which will estimate the slope at x. Okay, so let me plug those in. So instead of y2 minus y1, let's see, let me label these, x1, y1, x2, y2. And I'm going to plug them in. So the slope of the dark blue line, y2, the f of x plus h minus y1, f of x, over top of x2, x plus h, minus x1, x. So in pink, that is the slope of that blue line, estimating the slope at x. I can simplify this even further. If you notice, the denominator and x minus x cancels out. So I have the f of x plus h minus f of x, y2 minus y1, over just h. That would be a good estimate for the slope at x. Okay, however, as I demonstrated before, the slope of the blue line is much steeper than the slope of the red line, specifically at x. So what if I did this? Rather than my secant line going as far to the right as I went, I bring it a little bit closer. So I shrink down my x plus h distance. So instead of being all the way to the end of the function, maybe it's only halfway. I'm still trying to estimate the slope at x. And if I look at this, I can see that the slope of that blue line is a heck of a lot closer to the slope of the red line at x. It's still steeper, but it's closer. Maybe I can get a better estimate by moving that point even closer. So let's bring this dot down here, and then that's going to shrink this down. And now the slope of that blue line is pretty darn close to the slope of the red line at x. In fact, they're almost looking parallel. I could be even more accurate. I could bring this second dot so close that the distance in between the two dots is infinitesimally small, really, really tiny. Well, if I did that, then my estimate would be extremely accurate. The closer these two dots are to each other, the closer the slope of the blue line mirrors the pink line, which is my slope at x. Well, if I let that distance between the 2 points get closer and closer to 0, or I would say the limit as h, the distance between the 2 points approaches 0, I could then find a limit approach to the definition. So I could say the limit as h goes to 0, the horizontal distance between my 2 points gets infinitesimally small, and then I could calculate the slope formula. This is the limit definition for slope. This is the slope of the tangent line, which is also the derivative. So I used the slope of the secant line, making the horizontal distance really, really small, to eventually pretty much equal the slope of the tangent line. So now my estimate is really, really accurate because I have a small incremental change. And that's all calculus is, the study of small change. So this is the limit definition of the derivative, which is the slope of the tangent line at that point, which is also known as the derivative. So we're saying the same thing 3 different times: the limit definition, the slope, and the derivative. And you can even go one step further. That's the instantaneous rate of change. That's saying how fast is that red curve moving exactly at x, because it's moving at different speeds throughout the entire function. Let me give you a real life example of that. You're driving your car down the road, and you're driving from your house to a store somewhere. You got to go down your driveway, down your street, get on the highway, eventually make your way to the parking lot. You have different speeds along the way. So your speeds are different throughout your entire trip. So your instantaneous rate of change would say, how fast am I going at a very specific point in time? Let's say I leave my house at 1 o'clock and I get to the store at 1:15. How fast was I going at exactly 1:07 o'clock? Well, if I look at the speedometer on my car, it'll tell me I was traveling at 32 miles an hour. 32 miles an hour is your instantaneous rate of change. It's your instant speed. That's your derivative. In your car, your speedometer is a derivative machine. It gives an instantaneous rate of change, which is the slope of the tangent line, which is telling me how fast my car is moving exactly at that moment in time, because at a different moment in time, I'm going to be moving at a different speed. That's all derivatives are. Instantaneous rates of change. Visually, slopes of the tangent lines. And it comes from the formula that I circled as the limit as h goes to 0, f of x plus h minus f of x over h. So that's what a derivative is. Now, the calculation might be a little bit more involved, but essentially, that's the basis of calculus right there. Knowing what a derivative is, as to me, is as important as how to calculate a derivative. So let me spend a couple seconds here and just practice calculating a few different derivatives. All right, let me go back to my original picture that I had with you guys. Okay, this was the original function that I was interested in finding the derivative at a specific point that I called x. Okay, let me change this just to make life a little bit easier. Let me bring this curve down. And instead of just calling that f of x, let me tell you that that f of x happened to be x squared. Okay, let's calculate the derivative of x squared using the limit definition. So then I'm going to have to calculate the limit as h goes to 0. And then here's the equation that I'm using in green, the f of x plus h. So what I'm doing is plugging in x plus h into this function. So I'm going to swap out my f of x plus h, and I'm going to actually plug that into the function that I'm finding the derivative of. So then this is going to be x plus h squared minus f of x. Well, instead of f of x, I use the function f of x, in this case, x squared. All of that over h. If I calculate this limit as h goes to 0, I would have the derivative. Okay, the easiest way to calculate derivatives is to plug in a 0. But you can see when you go to plug in this 0 for h, you get a divide by 0 error. So you can't plug in a 0 until you algebraically manipulate it to divide that h out. So what I'm going to do is I'm going to expand the numerator. X plus h squared is x plus h times x plus h, which would be x squared plus 2xh plus h squared. The shortcut to squaring a binomial, I square the first term, I double the product, I square the last, in case you can't remember how I did that in my head, or you multiply x plus h times x plus h. Minus x squared comes down, divide by h comes down. I still can't plug in as h goes to 0 because I have a divide by 0 error. But look at one thing that's occurred. These x squareds are going to cancel each other out. X squared minus x squared goes away. So now I'm left with limit as h goes to 0. One more thing I want to do. I have an 2xh in the numerator with an h squared. I'm going to factor an h out instead of just copying what I have. So I'm going to factor an h out of 2xh. I'll be left with 2x. I'm going to factor out an h from h squared. I'm dividing it out. I'm going to be left with h. If I distributed it back in, I'd get what I have up there in purple. When I factored that out, that now gave me an h in the numerator and the denominator that divide out and reduce. So now I can calculate the limit as h goes to 0, excuse me, for 2x plus h. I've divided out my divide by 0 error, and now I can plug in the 0 for h. And I would be left with 2x. So if the function is f of x equals x squared, its derivative is 2x. So I can say that f of x equals x squared. The derivative, notation-wise, is f prime of x equals 2x. So I have two functions here. I have the original function, that's in red, and I have its derivative in light blue. The derivative will tell me the instantaneous rate of change at any given point. For instance, if I wanted to know how fast was this function moving at 0, I can plug in a 0 into my derivative. I can find the f prime of 0. I would get 2 times 0 and get 0. So how fast is the function moving at 0, 0? It's not moving very fast at all. It has a derivative of 0. Its instantaneous rate of change is 0. That means the slope of that tangent line is also 0. Okay, well, let's go further down the line. What if I wanted to know the derivative at 2? I would want to be finding the slope of the tangent line at 2. Clearly not a slope of 0. The function is moving much faster now. Okay, so let's calculate using the derivative equation for x squared, the f prime of 2. 2x. 2 times 2 equals 4. So the derivative at 2 is 4. So the slope of that instantaneous rate of change, the slope of that tangent line, is 4. I'm going to go one more. What if I wanted to find the slope at 3? That's up here. And I can see that graph is much steeper now. So I can now use my derivative to calculate that. The f prime of 3, 2x, 2 times 3, x equals 3, is 6. The derivative is 6. So I had a slope of 0, a slope of 4, a slope of 6. The function is moving at different speeds at different places along the x-axis. And it's moving faster and faster and faster, and that's why the derivative is getting bigger and bigger and bigger. Back to my real world model. Here I am at 0, sitting in my driveway. I'm not moving. I'm getting in my car, and now I'm speeding up. And this is my times: 1 minute, 2 minutes, 3 minutes. My speeds are going from 0, 4, and 6. Whether that's in miles per hour is irrelevant. But that is a derivative, and that is a very basic example of what a derivative does for me. It finds the instantaneous rate of change, and it also finds the slope of the tangent line, because those two things are the same thing. So that's pretty much it for derivatives in a nutshell as far as the basics go. Now, as far as calculating derivatives, the more involved a function gets, the more involved calculating the derivative gets. But what I'm trying to do is give you a function and then ask you how fast is it moving. Well, you calculate the derivative. That's a second function that calculates how fast the original function is going. That's the basis of calculus. All based off of that limit definition as h goes to 0 for the f of x plus h minus f of x over h, where h was that horizontal distance getting smaller and smaller and smaller, allowing my secant line to become a better and better and better estimate of my tangent line. Hope that makes sense, and hope your head isn't spinning too much. If it is, watch this again. It might make sense the second time. Thanks.